And let's move on to the vector. So from vectors, where we are going to talk more about the structure for data. Well, in order to explain vector, we need to start our discussion from scalar. So scalar is any singular value, and it is any kind of natural number or any kind of number that we have been dealt with. So integer or any real rational number or whatever, 1, 3.14, or any unknown that whose domain is a real number. Let's put it in this way. So variables who have a specific domain, well, these are called as scalar. And let's move on to vector. So vector is a collection of these scalar values, but they have some kind of order. So this is different from set. Set a collection of those numbers, but you don't have any order in the set. And by definition, set does not allow you to have duplicate. But vector, where if you have x1 to xd like this, where the order is important. And also there are duplicate. That means x1 could be equivalent to x3, x4 could be equivalent to x5, something like that. And in terms of notation, where we can put vector in this way. So within parentheses, x1 to xd. And in a shorthand notation, where sometimes we put an arrow on top of the variable. But at the same time, sometimes we use a bold case. So simply put the character in boldface, where it will give us the notation for the vector. And to understand what vector is, well, let's start from a directed line segment. So let's suppose you have a line stop, and it is starting from a point, and it goes to another point. So starting from A, it goes to B. So in order to represent everything that I just mentioned, you need to know where it starts, and you need to know the direction. So the location of B from A. And you need to know the length of that line segment. And now let's talk about vector. So vector is an abstraction of what we just discussed. So vector is an abstract of a line segment. Well, why it is abstract? Because we only want to focus on direction and magnitude. So, well, again, well, basically we don't say the starting point of every vector. So we don't know where it starts, but we know the direction and we know the magnitude or length. And in case you want to visualize a vector, so it is represented as a line segment, but we suppose all the vectors are starting from the origin. So starting from this origin where A1 and 2, where we can imagine it is going to where somewhere A2, A1 and A2, and that looks like this. Well, given that if you have two different vectors, where you are able to compare them, in order to compare them, you need to have same length. So you have two vectors x and y. Their dimensionality should be the same. So both vectors should have the same number of elements. And in order to say those two vectors are the same, well, you need to conduct an element-wise comparison. So you need to compare x1 and y1 are the same, x2 and y2 are the same, blah, 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 or xd to yd are the same. And visually, well, there could be some cases. So here are two vectors, A and B. In this case, A and B, they are going to the same direction, but where their magnitude are different. So in this case, those two are different vectors. Where in example 2, you have two vectors, but they have same magnitude, but they are going to different direction. So in this case, again, they are different vector. Where example number 3, they are going to the same direction and their magnitude are the same. So in this case, where these are the same vector. And talk about the vector operation. So addition, again, you are playing element-wise. So x1, y, well, in order to add x and y vector, you need to add x1 and y1, x2 and y2, blah, 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 xd and yd. Subtraction is the same. You need to perform element-wise operation. And scalar multiplication, where in front of the vector, you have a scalar value. In this case, you are distributing this scalar value into every other element in the vector. So k, it goes to every element of the vector. And speaking of inner product, this is really, really important. So well, in the later slide, I have designated a section for that. Inner product, people use this kind of bracket to represent inner product operation. And I like this dot operation a lot more. So people call this as dot product as well because we use this sign. And in terms of the linear algebra notation, basically you have two vectors in the same shape. And in order to make this multiplication work, you need to change the shape of one of the guys. That operation is called the transpose. So you have two vertical vectors, and you need to make it two horizontal vectors, and you need to make it vertical. So that is called the transpose. So, well, if you have taken linear algebra, well, this should be familiar to you. Well, anyhow, well, x transpose y or y transpose x, they are equivalently saying the inner product of x and y. And essentially what we do is element-wise multiplication and take the summation of them. Well, we have inner product on one hand. On the other hand, we have outer product. So notated using this. And it is making sort of cross product of every other element. So x1, x2. And next element should be x1 multiplied by y2. Next element x1, y3, and so on. And if you go below, the second element right below x1 and y1 is x1, y2. Next is x1, y3, and so on. So you got the idea. And basically, you are enumerating all possible combination of the element of x and y. And when we talked about vectors have direction and magnitude. And in order to calculate the magnitude, we often use a distance called as Euclidean distance, or in some cases we say it as a norm, so Euclidean norm. So you have a vector, and norm is meaning the magnitude in a certain way. So that is represented by this. So the magnitude is notated using these two bars. So you're surrounding a vector with bars. And that is basically inner product of itself and taking the square root of the inner product. And they can be represented in this way again. So you're going to make the square sum of every other element. And at the end of the day, you're taking the squared root. And speaking of the meaning of this Euclidean norm, where you must be familiar with this. So basically you have a vector. And this vector 5 and 3. And in order to calculate the magnitude of this vector, very simple, where 5 to the 2, 3 to the 2, take the sum, take the root square. Well, we are going to say a lot more things about this norm. So we are going to talk more than Euclidean norm. So, well, from the middle school, we didn't ask why we need to scale them and things like that. But there are actually different variations in this norm notation. So there is one norm, that is Manhattan norm, and two norm, that is what we are familiar with, Euclidean norm. And there are three norm and so on. So basically, it is generalized as P norm. And there is another special case that is infinite norm, that is basically taking the maximum value out of the vector element. So, well, each of these have some special meaning, and depending on the meaning, well, you can utilize them in different contexts in machine learning. Let's talk about the distance between two different vectors. So, distance could be measured as the difference between, these. And especially the difference is measured as x minus y. And if you do so, then it has a direction, something like this. So I believe I prepared the animation for that. So xy can be represented in this way. And we want to measure the distance of xy, x minus y. So distance is norm. So basically this is representing distance. And E is from Euclidean. And well, in the previous page, we have seen the notation for two norm. And calculating the Euclidean distance is putting the vector x minus y into the notation of two norm. So basically, you can end up with a notation like this. And again, this distance notation can be generalized. So one norm could be looks like this. Two norm, what we just have seen. So this is something we are familiar with. And infinite norm, basically taking the maximum dimension value. And we can visualize the distance in this space. So in the case of one norm distance, that is have a special nickname that is Manhattan distance. So if you go to the city Manhattan in New York, where everything is planned and everything is in really nice grid shape. So if you want to go from one place to another, well, if you would go in this direction, that is going to be really happy because this is the shortest distance. In this case, we could measure the Euclidean distance by taking the direct length between A and B. But this is not possible in New York because there are a bunch of different buildings. So you cannot go into the building as you want, and you have to go around the building. So maybe you take this route. So calculating the distance that is taking the detour like this, that is called as Manhattan distance. And interesting thing is, whatever make the choices, so you can go this way, or you can go this way. Let's move on to this diagram. So you want to make a travel from point A to point B. Whatever you take, so where this is red path, or this is yellow path, or blue path, where all the distances are the same. So Manhattan distance is basically signifies the detouring distance. Again, this yellow line is Euclidean. So that is a quick summarization in visual. And on the Cartesian product, well, this is a rather important concept to understand. So later on, we are going to play with the norm to regularize your model. So in that case, well, you need to understand the meaning of each norm better. So say you have 2 points. One is here. I'll say A, B. So L1 distance or L1 norm, basically you're taking this rectangular move and measuring the distance, that is L1 distance, P1. This diagram is saying something different, sorry. So we are taking the difference here. So sorry about that. In this diagram, L1 is this direct distance, and L2 is making a circle. So suppose you have a circle and A, B are two different points on that circle, and L2 distance is basically measuring the distance on the circle. And from these two cases, we can make an induction. So, sorry, as the value P grows, you're basically making this angle more aggressive. So this was P2, and it is going to the outside more as P gets larger. So we will come back to this idea when we talk about regularization. So, well, let's bookmark it and let's move on. And let's talk about inner product. So basically this is the product of a vector, but this case, we are considering more on the magnitude of the vectors. So notation-wise, well, we have seen these two. But in terms of computation, well, we can take this detour. So you can come up with the magnitude of x and magnitude of y and multiply them with cosine theta. Theta is the angle between vector x and y. And same result could be obtained using component-wise operation. So this is what we have seen. So x1, x2, x1, y1 plus x2, y2, where this is given. But given that we can calculate cosine theta solely. So out of this inner product value, if you divide them using two magnitudes, so inner product over magnitude, then you can calculate the cosine theta value. And this gives us a lot of interesting stuff. So, well, from middle school, we studied this Cauchy-Schwarz, inequality. And this is basically saying inner product square is smaller than inner product of each vector themselves multiplied. And we can make a simple proof for this guy. Well, the proof is really, really simple. And once you know it, this is thing. So, well, try to put your doubt on it and try to prove it yourself. Next class, we are going to discuss it. And at the end of the day, the result can be summarized in this way. So, well, we are speaking of the angle, and inner product could be obtained using this way. The angle is very important to decide the value of inner product. And we can make some kind of conclusion out of lots of aspects. So, well, if two vectors are going to opposite direction, then we can say the angle is 180. In that case, cosine is minimized. Cosine is minimized because cosine is ranging between -1 and 1. Since cosine is minimized, my inner product is minimized as well, given two different vectors. Let's talk about the opposite case, where there are two vectors going to the same direction. In that case, those two angle 0. When angle is 0, cosine is 1, and that is the maximum value for the cosine. In that case, we can say the inner product given two different vector magnitude that is maximized. Well, somewhere in between, so there are a bunch of different, infinite number of possible angles. where it is basically somewhere in between. So we can try to make additional conclusions. So this gives us a notion of similarity. There are two different vectors. We know the magnitude. Depending on the inner product value, we can say they are similar or not similar. So inner product value is proportional to the vector similarity. So we can sort of draw out this kind of a diagram. So to this end, this is less similar. To the other end, this is more similar. And inner product is used everywhere in machine learning. So you will get in love with inner product throughout the semester. So this is one slide from linear regression. This is one slide from neural network. And linear regression is one of the models that we are going to learn soon. And neural network is some of the model that we are going towards the end of the semester. That means where we are going to play with the inner product throughout the semester. And let's move on to the projections and basis. So speaking of multiple vectors, one of the important idea that we want to understand and we want to be able to exploit is the concept of orthogonality. So basically orthogonality means something perpendicular. So you have two vectors and they are meeting or they are starting from somewhere, but they're heading to two different directions and their angles are 90 degrees. So orthogonality, where in terms of cosine value here, we're given an inner product value between x and y. If x and y are orthogonal, well, the angle is 90. So cosine 0 value is going to be 0. That means the inner product value becomes 0. And there is one additional concept that we also want to understand. So while you read the textbook or some articles, where if you see this vocabulary, then you need to understand what it is. So basically, orthonormal vector, you have two or multiple different vectors, but all of these are orthogonal. So they are meeting at 90 degrees each other. And each of them, magnitude is 1. And using the idea of orthogonal or orthonormality, then we have multiple different methodology built up. So one of such is getting a projection vector. So the idea of a projection vector is where you have given two different vectors, A and B. Let's assume you have an extended line like this, and this extended line is meeting with the vector B. And the angle between this extended line and the vector B is 90 degrees. In this case, we can measure the distance of a vector from here to here. And this is something like a shadow of vector A on vector B. This is a sort of informal definition, and it actually has a specific name, which is projection. And it even has a notation. So project B on A. And this slide is actually covering how to come up with this computation. So basically, you only need to memorize this formula. And this formula means actually many things though. So it consists of a new vector U, and U is called as a unit vector. Unit vector is just a vector itself over the magnitude of the vector. Well, if you do so, then you're going to have a vector whose direction is the same as x, but the magnitude is 1. Well, understanding that computing the projection is quite straightforward. So, well, you have a unit magnitude and same direction as x. This is what we just discussed. And you multiply u onto y. And it's going to be the magnitude of the projected vector. And at the end of the day, we want to multiply magnitude of the projected vector. So this is yt, u1, and the direction of x, which is u1. So well, this is going to be the projection vector. So projection of y on vector x. So here comes the important idea. So well, in linear algebra, well, in my opinion, linear algebra consists of three key chunk of the topics. So one is the basic operation, so basic definition and operation. And number two is how to address the system of the linear equation using linear algebra or using matrix easily. So system of linear equation is well, 연립방정식 in Korean. And number three is bunch of decomposition. And basically decomposition. So well, this is in my idea, well, sort of categorization of the topics in linear algebra. And number three, decomposition. Where decomposition is meaning given a matrix, we'll try to separate this into factorization of multiple matrices. Maybe. So decomposition, factorization of A matrix into multiple smaller matrices. So well, one of the prerequisites for this course is linear algebra, so I'll just draw the names of the decomposition. So LU decomposition and QR decomposition and eigenvalue decomposition, singular value decomposition, or PCA, principal component analysis, where all these things are sort of decomposition. And they have some sort of shared purpose. So eventually, if you use QR decomposition and eigenvalue decomposition, or singular value decomposition, then you're going to get a matrix that consists of multiple orthonormal vectors. So again, these are orthonormal. Means that well, any pair of UI, well, I'm gonna write them down. So we just discussed the meaning of orthonormal in few slides ago. So any pair of UI and UJ in this set is perpendicular. And also the magnitude of any UI is 1. So many of these decomposition, the purpose is to get the orthonormal vector. And well, having orthonormal vector has some meaning. So you can explain your space more effectively. So this means where you have your own coordinate system in terms of the U vector. well, imagine you have multiple different data points in a, well, along with the same line. In order to represent all those data points, you need, well, for each of them, you need two numbers because they are data points on two-dimensional space. But if you take the eigenvalue decomposition, then you can find out where there is a vector that is going through to the data. And this is going to be your principal component. And since every data point on the principal component, well, you don't need to use the original coordinate system. You only need a scalar value on the principal component. So one of such analysis is QR decomposition. So in QR decomposition, you have the input matrix A, and you're going to decompose the original matrix A in terms of a matrix Q and another matrix R. And normally in linear algebra, if you see a matrix notated in Q, that is orthonormal vectors. And well, there is a fun fact. So the original name of this decomposition is indeed QU decomposition because we have a Q matrix and U matrix. That means upper diagonal matrix. But QU matrix sounds a lot similar to Q matrix, so it's going to be very confusing. So people change the name to QR decomposition. Well, anyhow, well, Q is the orthonormal vector. So this is representing a new coordinate system. And U matrix is well, sort of coefficient on this Q coordinate system. And the key idea is where if you decompose the original matrix A into Q and R, where lots of other computation involving Q and R instead of A is going to be much more efficient. So that's the main idea. So Gram-Schmidt autonormalization, so this is how you compute the QR decomposition. So where you have a matrix, given set of vectors, so matrix, you want to find the orthonormal basis for the vector space. So this is a coordinate system for the input matrix. Well, the computation, well, the detailed computation I already went through in the slide. So if you just follow the computation on the slide, then you can understand the detailed process. Here, I would like to highlight the idea. So initially, you have vectors like this. And the idea is where you want to make this as orthonormal vectors. And the idea is starting from the first vector, x, where you just to build a unit vector of the x. And you try to come up with the u2, Well, this is representing the second original vector. But if you look into the computation, you first try to explain x2 using u1 and take the difference between the original x2 and this projection. So we can say this projection x2 on x1 is the information of x2 explained by x1. And you want to take the difference between the original x2 and the projection. And it's going to be normalized eventually, and that's going to be u2. And later on, you're going to do the same thing cascadingly. So for every xi, you first want to try to explain the vector itself using the projection of the earlier vectors. And then ui is going to be the normalized value of the remaining information. So this is QR decomposition, well, the idea behind the QR decomposition. So again, we started our discussion from where orthogonality and orthonormality, where these two are the important concept. And we try to understand how to compute the projection of a vector to another vector. So these are basic operation and basic concepts. And then we moved on to independent vector set or orthonormal vectors. And we discussed where if you have an orthonormal vector for a vector space, then we can, well, it's like we have a new coordinate system that is more efficient to the vector space. And QR decomposition is a way to come up with such orthonormal vector. So new coordinate system for a given vector. Given vector A is decomposed into Q, and the coordinate on the vector space, that is R. And Gram-Schmidt's orthonormalization is the way to compute QR decomposition. So, well, detailed computation with an example is following.